Somewhere inside the Linux kernel, in a small piece of locking code written back in May of 2011, a mistake has been sitting quietly for 15 years. It's shipped in every mainstream Linux distribution since then: your desktop, your phone if it runs Android, cloud servers, shared web hosting, container platforms, essentially anywhere the Linux kernel runs. Nobody noticed. Nobody exploited it, as far as anyone can tell. And then, this past July, a security research team turned it into a working exploit that takes an ordinary, unprivileged local user from zero access to full root control of the machine in about 5 seconds, with a 97% success rate. Think about that timeline for a second. 15 years is longer than the entire lifespan of the iPhone. It's long enough that entire generations of hardware have come and gone. Entire companies have risen and fallen, and an enormous amount of the world's computing infrastructure, the servers running websites, the cloud instances powering apps, the Android phones in people's pockets, has been quietly carrying this exact flaw the entire time, completely unnoticed by anyone, malicious or otherwise. They're calling it GhostLock. And understanding exactly what it is, how it works, who it actually affects, and what you should genuinely be worried about versus what's overhyped is worth a proper, careful look. Because this is exactly the kind of story that's easy to either panic over or dismiss too quickly, and neither reaction gets you to the right answer. Let's start with what GhostLock actually is, at a technical level, because understanding the mechanism matters here more than just knowing it's bad. GhostLock, formerly tracked as CVE 2026-43499, is what's called a use-after-free vulnerability, sitting inside the Linux kernel's real-time mutex code, specifically inside a function called remove waiter, part of the kernel's futex priority inheritance locking subsystem. That's a lot of technical terminology at once, so let's unpack it piece by piece, because each piece actually matters to understanding why this bug is as serious as it is and why it took 15 years for anyone to actually notice it. A futex, short for fast user space mutex, is the Linux kernel's standard mechanism for letting programs coordinate access to shared resources between multiple threads. The entire design philosophy behind a futex is efficiency. Most of the time, when a thread needs a lock, it can grab and release that lock entirely in user space without ever bothering the kernel at all. The kernel only gets involved in the specific case where a thread actually has to wait for a lock that's currently held by something else. That efficiency is exactly why futexes are used so pervasively. They're the underlying mechanism beneath an enormous share of ordinary multi-threaded software running on Linux systems every single day, from your web browser to a database server to the container runtime managing your cloud infrastructure. Nearly every piece of software you've ever run that does more than one thing at once is, at some level, leaning on this exact mechanism without you ever needing to know it exists. Priority inheritance is a specific, more advanced feature built on top of that basic futex mechanism, designed to solve a subtle scheduling problem. If a low priority thread is holding a lock that a high priority thread needs, the low priority thread can end up getting stuck behind other unrelated threads, effectively blocking the high priority thread indefinitely. A problem called priority inversion. Priority inheritance solves this by temporarily boosting the low priority thread's priority for as long as it's holding the contested lock, ensuring it finishes and releases the lock promptly rather than getting starved of processing time by unrelated work. It's a genuinely important feature, especially for real-time and latency-sensitive systems, and it's compiled into essentially every mainstream Linux kernel built by default through a configuration option called config futexpi. Here's where the actual bug lives. The remove waiter function is a cleanup routine that runs when a thread waiting on one of these priority inheritance futexes needs to be removed from the wait queue. For instance, if the wait times out or gets interrupted. The flawed code makes an assumption that turns out to be unsafe under a specific set of conditions. It assumes the thread currently executing this cleanup routine is always the same thread that's actually being cleaned up. Under normal circumstances, that assumption holds, but a specific kernel operation called a requeuepi, which moves a waiting thread from one futex to a different one, a legitimate and fairly common operation used by certain synchronization patterns, can create exactly the mismatch scenario this cleanup code doesn't correctly handle. When that mismatch occurs, the kernel ends up operating on the wrong task state entirely, leaving behind a stale, dangling pointer to memory that's since been freed and potentially reused for something else. That's the use after free at the heart of GhostLock, a scenario where the kernel accesses memory it no longer legitimately owns, based on state it incorrectly believes still points to a valid, currently running task. To make that concept a little more concrete, imagine a hotel that assigns a specific staff member to clean a specific guest room once the guest checks out, based on the assumption that the person doing the cleaning is always the same person who was actually managing that particular room. Now, imagine a scenario where guests occasionally get moved between rooms mid-stay, a legitimate, normal operation the hotel supports, but the cleaning assignment system doesn't correctly track that a swap happened. The cleaning staff ends up going into the wrong room, one that may have already been reassigned to a completely different guest, and starts acting on outdated information about who's supposed to be there. That's roughly the shape of the mistake sitting inside remove waiter, cleanup process operating on the wrong target because a legitimate reassignment operation elsewhere in the system wasn't properly accounted for in the code responsible for cleaning up afterward. An attacker who understands this precise mismatch can deliberately manufacture the exact sequence of Futex operations needed to trigger it, then use the resulting use after free condition to manipulate kernel memory in a way that ultimately grants their own unprivileged process full root privileges. Nebula Security, the research team that disclosed this vulnerability, built a working, full-chain exploit doing exactly that, and reported it reaches root from a completely unprivileged starting process in roughly 5 seconds, succeeding about 97% of the time in their testing. It's worth pausing here to appreciate just how unusually clean and reliable that exploit performance actually is, because it's not typical even among serious, high-severity vulnerabilities. A lot of real-world kernel exploits, even ones rated as critical, end up being finicky in practice, dependent on precise timing windows, specific hardware configurations, or memory layouts that vary unpredictably between different systems, making real-world reliability considerably lower than a controlled lab demonstration might suggest. A 97% success rate, reaching full root in about 5 seconds, represents an exploit that's been engineered to a genuinely high degree of practical reliability, which is exactly why security teams across the industry treated this disclosure with real urgency, rather than filing it away as a theoretical, hard-to-actually-use concern. That level of reliability also matters enormously for how quickly a vulnerability like this can realistically get weaponized by attackers who aren't the original, sophisticated research team that found it. A finicky, unreliable exploit that only works under narrow, specific conditions requires real skill and effort to actually deploy against real targets, which naturally limits how quickly it spreads through the broader landscape of malicious actors. A clean, highly reliable, publicly published exploit removes almost all of that friction. Anyone with basic technical competence can pick up the published proof-of-concept code and have a reasonable expectation. It'll actually work against an unpatched target, which is precisely why security researchers have been treating the window between public disclosure and widespread patching as genuinely urgent, rather than a slow-burning, lower-priority concern. Let's talk about scope, because affects every mainstream distribution for 15 years is a genuinely enormous claim, and worth being precise about exactly what that does and doesn't mean. The vulnerable code was introduced into the Linux kernel in version 2.6.39, released back in May of 2011, and the vulnerable range extends all the way up through kernel version 7.1, right up until the point the actual fix was merged. That means essentially every Linux kernel shipped by any mainstream distribution over the past decade and a half potentially contains this flaw, provided that kernel was built with the config Futex PI option enabled. And here's the important detail. That option is enabled by default on every major Linux distribution. It's not some obscure, rarely used configuration flag that only specialized systems turn on. It's standard default kernel configuration, present because the priority, inheritance mutex functionality. It enables is something ordinary software across the ecosystem genuinely depends on. You can't simply disable this feature on a running system without breaking real, legitimate software that relies on it, which is exactly why this isn't a bug you can patch around with a quick configuration toggle. The fix has to come from an actual kernel update. Given that default configuration, the practical affected population is genuinely enormous. Desktop Linux distributions, Android devices at the kernel level, cloud server instances across every major provider, shared web hosting platforms, container runtimes, CI and build infrastructure, essentially anywhere a standard Linux kernel is running with default configuration, which describes the overwhelming majority of Linux deployments in the world. It's worth pausing on that Android detail specifically, since it's easy to overlook in a story that mostly gets framed around servers and desktops. Android's kernel is itself a modified version of the Linux kernel, and the priority inheritance Futex code sits deep enough in core kernel infrastructure that it's plausible for this same underlying vulnerability class to extend into at least some Android. Kernel builds too, depending on exactly which kernel version and configuration a given device manufacturer shipped. That's a genuinely enormous additional population of devices worth being aware of. even though the primary security advisories and patching urgency documented so far have focused mainly on traditional server and desktop Linux distributions specifically. There's a specific detail about this bug's disclosure timeline worth understanding, because it changes how urgent the situation actually is compared to a true, unexpected 0 day. GhostLock is what's called an N-day vulnerability, not a 0 day, meaning the flaw was reported to the kernel maintainers privately, fixed, and had that fix distributed through official channels before the public disclosure and proof of concept exploit became widely available. The specific timeline here: the vulnerability was reported on April 18th of this year, fixed upstream in the kernel just 2 days later on April 20th, and that fix had already been backported into various distribution-specific kernel builds by May 4th, all well before Nebula Security's public disclosure, complete with working exploit code, went out on July 7th. That timeline actually matters quite a bit for how you should think about your own personal risk level, because it means official patched kernels have genuinely been available for a meaningful window of time already, for anyone who's been keeping their systems reasonably current with routine security updates. The real risk this story highlights isn't primarily about some brand new undiscovered flaw nobody could have possibly prepared for. It's specifically about the gap between when a fix becomes available and when any individual system actually applies it. That gap, sometimes called patch lag, is where the genuine danger in this specific story concentrates, now that a reliable public exploit exists for anyone motivated to use it against machines still running an unpatched kernel. It's worth being precise about which specific systems have already received patches and which haven't, since the picture varies meaningfully across the Linux ecosystem rather than being uniform. As of recent reporting, patched kernels were already available in production for Alma Linux, Red Hat Enterprise Linux, and Debian 13. Ubuntu's long-term support releases, 22.04 and 24.04, along with Debian 11 and 12, were still listed as either vulnerable or actively in the process of receiving their patches at the time of that reporting. That's an important practical distinction. If you're running one of the distributions still working through their patch rollout, your actual exposure window is meaningfully longer than someone running an already patched distribution. And it's worth checking your specific distribution's own security advisories directly, rather than assuming any single blanket statement applies uniformly across every Linux system everywhere. Let's talk about who should be genuinely worried about this, because the honest answer depends heavily on your specific situation, not a blanket everyone panic framing. The core nature of this vulnerability, a local privilege escalation, means an attacker needs some way to already be running unprivileged code on the target machine before they can use GhostLock to escalate that access to full root. This isn't a remote, network-facing vulnerability that lets someone break into your machine from across the internet with no prior access at all. It requires local code execution as a starting point. That's an important nuance worth sitting with, because local privilege escalation sometimes gets misunderstood as automatically less serious than a remote vulnerability, when in practice, the real-world danger depends entirely on how easy it is for an attacker to obtain that initial local foothold in the first place. On a personal computer, used only by its trusted owner, obtaining that local foothold is genuinely difficult. An attacker would need some other way in first, like tricking you into running malicious software. But on a shared multi-tenant system, that local foothold is often trivially available to begin with, because the entire point of the system is running code from many different mutually untrusted parties on the same physical or virtual machine. That's exactly why a local privilege escalation bug like this one can be just as dangerous in practice as a remote vulnerability, depending entirely on the specific environment it's running in. That distinction is exactly why certain specific environments face dramatically higher real-world risk than others. Shared hosting environments are a genuinely serious concern, because the entire security model of shared hosting depends on isolating different customers' accounts from each other on the same physical or virtual machine. If one customer's website gets compromised through some unrelated vulnerability, GhostLock could let that attacker escalate from controls one compromised website to it has full root access to the entire shared server, suddenly putting every other customer's site on that same machine at risk too. Multi-tenant cloud environments face a similar structural risk. Container platforms and Kubernetes clusters are specifically worth flagging because GhostLock has been confirmed to work as a container escape as well, meaning a compromised container, which is normally supposed to be isolated from the underlying host system, can potentially use this exact vulnerability to break out of that isolation and gain root access to the host machine itself, turning what should be a contained, limited incident into a full host compromise. CI and build infrastructure, where untrusted or third-party code frequently gets executed as part of automated pipelines, represents another genuinely elevated risk category for exactly the same underlying reason. By contrast, a personal desktop or laptop used by a single trusted individual who isn't running arbitrary, untrusted code from unknown sources faces meaningfully lower practical risk from this specific vulnerability. Not zero risk, since patching promptly is still clearly the right move, but a different risk profile than a multi-tenant server handling code or workloads from parties you don't fully trust. It's worth mentioning something genuinely unusual and worth appreciating about how this vulnerability was actually found and disclosed, because it reflects a healthy, functioning part of the security research ecosystem, rather than a purely alarming story. Nebula Security discovered and reported this vulnerability through Google's Kernel CTF program, a bug bounty initiative specifically designed to reward researchers for responsibly finding and reporting exactly this kind of serious kernel vulnerability, rather than exploiting it maliciously or selling it to the highest bidder on some underground market. For their work, Nebula Security received a payout of over $92,000 through that program. That's a meaningful, tangible example of the responsible disclosure process working roughly as intended. A serious flaw gets found by researchers with a financial and reputational incentive to report it properly. It gets fixed by kernel maintainers within days of the initial report, gets distributed through official channels to distribution vendors, and only becomes public knowledge, complete with proof of concept code, after that whole responsible process has already played out. That's a meaningfully better outcome than a scenario where a similarly serious flaw gets discovered by a malicious actor and used quietly without ever being reported or fixed at all. It's worth appreciating just how fast the actual fix turned around here too, since that speaks well of how the kernel security process functioned in this specific case. 2 days between the initial private report and a merged upstream fix is genuinely fast, even by the standards of a project as large and actively maintained as the Linux kernel. That rapid turnaround gave distribution vendors a meaningful head start, nearly 3 months in fact, between the fix landing upstream and the public disclosure, to get patched kernels built, tested, and rolled out through their own official update channels before anyone outside that responsible disclosure process even knew the vulnerability existed. Whether every individual system administrator actually took advantage of that head start by applying updates promptly is, of course, a separate question, and exactly the gap this story is really about. That said, once a working exploit is public, and Nebula Security has indeed published their proof of concept code publicly as part of standard transparent security disclosure practice, the calculus does shift somewhat. At the time of the most recent reporting, there was no confirmed evidence of GhostLock actively being exploited in the wild by malicious actors. But security researchers have been direct in describing this as a race condition, in a different, non-technical sense of that phrase, a race between defenders, getting patches applied across the enormous, diverse population of affected systems, and attackers incorporating this now public, highly reliable exploit into their own malicious toolkits. Given how reliable and fast the exploit actually is, the expectation among security researchers covering the story has been that weaponization by real attackers, if it hasn't already begun quietly, is likely imminent, which is exactly why the practical advice across virtually every security bulletin covering this vulnerability has been consistent and urgent. Patch now, don't wait. That specific phrase, patch now, don't wait, has shown up nearly verbatim across advisories from Alma Linux, Red Hat, Cloud Linux, and independent security researchers covering this story, which is itself a notable signal. When multiple independent organizations covering the same vulnerability from different angles all converge on the exact same urgent recommendation, that consistency is worth taking seriously as a genuine signal of severity, rather than any single source simply overstating the risk for attention. So what should you actually do with all of this information, depending on your specific situation? If you're running a personal Linux desktop or laptop, the straightforward, low-effort action is simply making sure your system's regular security updates are current. Most desktop distributions handle kernel updates through their normal update mechanism, and applying those updates promptly closes this specific vulnerability, along with whatever else has been patched in the same update cycle. A quick check of your running kernel version, compared against your distribution's published list of patched versions, tells you definitively whether you're covered rather than leaving you to guess. If you're managing servers, especially anything involving shared hosting, multi-tenant infrastructure, or container platforms running workloads from multiple different sources or teams, this deserves genuinely urgent, prioritized attention rather than waiting for a routine, already scheduled maintenance window. Checking your specific distribution's security advisories, confirming whether the specific fix, tracked under the kernel commit 3FD63936DD, has actually been applied to your running kernel, and prioritizing that patch ahead of other less urgent maintenance work. For anyone running Red Hat Enterprise Linux or a compatible distribution specifically, checking your kernel version against the specific fixed builds your vendor has published. For instance, particular version numbers have been specifically identified as the fixed builds for certain enterprise Linux release streams. Gives you a precise, verifiable answer, rather than relying on a general sense that updates have probably been applied at some point. It's also worth understanding that there's genuinely no clean, temporary runtime mitigation available for this specific vulnerability, short of the actual kernel patch itself. Because the vulnerable priority inheritance Futex code is compiled directly into the kernel and can't be safely disabled on a running system without breaking legitimate software that depends on it, there's no equivalent of a quick firewall rule or a service restart that meaningfully reduces your exposure here. The only genuine fix is getting the patched kernel actually installed and running, which for most systems requires a reboot to take effect. Though some organizations running kernel live patching solutions may be able to apply the fix without that full reboot, depending on their specific infrastructure. If a full reboot genuinely isn't feasible in the immediate term for some operational reason, restricting local user access specifically to trusted accounts and ensuring container environments have properly configured security boundaries like seccomp profiles in place can meaningfully reduce practical exposure in the interim, though neither of those measures is a substitute for the actual patch, just a way to reduce risk while you work toward applying it. Stepping back from the technical details, I think this story is genuinely worth understanding for a broader reason too. Beyond just the specific patching advice, it's a useful, concrete illustration of just how much complexity and how much accumulated history sits underneath software that most of us treat as simple, stable, and thoroughly battle-tested. The Linux kernel is one of the most scrutinized, most actively audited pieces of software on the planet, worked on by thousands of contributors and reviewed constantly by security researchers specifically looking for exactly this kind of flaw. And a subtle, genuinely serious bug still sat quietly inside a core locking mechanism for 15 years before anyone found it. That's not really a criticism of the kernel's security practices. It's simply an honest reflection of how difficult it is to guarantee the absence of a flaw in software this large, this complex, and this deeply interconnected, no matter how much scrutiny it receives over the years. 15 years without discovery isn't evidence the process failed. It's evidence of exactly how subtle and specific the triggering conditions for a bug like this one actually were. It's worth thinking about how many similarly subtle interactions exist across a code base as large as the Linux kernel, which has grown to tens of millions of lines of code across its decades of development. GhostLock specifically required a particular, non-obvious interaction between a common cleanup, routine, and a less commonly exercised code path, the requeue PI operation, that most ordinary testing and code review simply wouldn't have stumbled onto without either extraordinary luck or the kind of deliberate adversarial thinking security researchers specifically bring to a codebase. That's genuinely the nature of security research at this level, finding the rare, specific interaction between two individually reasonable-looking pieces of code that, combined in just the right sequence, produces a serious flaw nobody designed or intended. I want to know how you're handling this one, if it applies to you. If you're running servers, shared hosting, or container infrastructure, have you already confirmed your patch status? Or is this the first you're hearing about GhostLock specifically? And if you're just running Linux on a personal machine, did this change how seriously you take routine kernel updates going forward? Tell me in the comments. I think stories like this are exactly the kind of thing we're hearing from people actually managing real infrastructure is more valuable than anything I can tell you in a video alone. If you want more grounded, technically accurate coverage of security stories like this one, explained clearly without either manufactured panic or dismissive hand waving, subscribe, hit the bell so you don't miss the next one, and I'll see you in the next video.